All right, next up, we have our final talk. It's going to be on technical transparency for AI labs by Daniel Reuter. So everyone give a round of applause for Daniel, who is coming up right now.
Okay, so this summer I have been working with Mauricio Baker at RAND on the following problem. How can a lab credibly assure third parties that some statement about its use of compute is true? And so the motivation behind this work is that if we can't get a solution to something like this, then it's going to be very difficult to curb race dynamics. So even if everyone in the world were able to come together and draft some big, beautiful set of rules on what AI development should look like, if we can't trust each other not to secretly break these rules, then due to competitive pressures, we are all just going to have to break these rules. And you could imagine that this will be even more of a problem once AI gets military applications. And so concretely, it would be great if labs could prove their compliance with some sort of global training pause. And so one way you might operationalize this would be to say that at the beginning, labs commit to the set of models that they currently have in their databases, they publish the hashes on the internet, and then they just continuously assure everyone that they are only running inference and only on those models. So they aren't running training anywhere on any of their servers. You might also want labs to be able to prove more semantically complex statements, or prove, for instance, that they aren't just using their inference fleet to compute some way to subvert this pause agreement. And so what you should visualize here is that what we need to do is we need to build some system that gets bolted onto existing lab infrastructure that just like extracts information out of it, just like says whether certain statements about what the lab is doing is true or false. And so this system will need to have two properties. One, it needs to be privacy preserving. Labs can't just spill all their beans, and it needs to be verifiable. So it needs to work even if the lab is trying to break it. And so in this talk, it's basically just going to be a whirlwind tour of conceptual work in progress. I'm kind of going to go fast, and then I'll throw in some technical work I'm doing at the end. Okay, so first of all, what's the overall setup? Here I'm just going to copy paste the standard interactive protocol setup from the security literature. Okay, so we are going to call this lab the prover. Okay, and so what the prover is it's some sort of computer system that is just doing a bunch of lab-like stuff. Okay, it's like it's got some inference servers, it's got some databases, it's all like everything's talking to each other. The details don't really matter too much. The point is that the prover has some secrets, and ostensibly, at least, it is supposed to be proving some statement about those secrets to this third party over here. And so the prover and the third party don't trust each other. And so we need to make a new computer system, which we will call the verifier, which sits in the middle of these two parties and somehow solves this problem for us. It's unclear how this will work, but that's the setup. Okay, and so generally, we're going to say that this system is one in which the prover issues a statement about its secrets to the third party. The prover and the verifier then exchange messages until the verifier is convinced that the statement is either true or false. These messages could be in natural language if these are intelligent algorithms, or they could just be like, simple messages, and these could be simple programs. And then at the very end, the verifier just emits one bit of a verdict with its decision about whether the statement is true or false. And so what makes this different from the standard interactive protocol setup is that these statements might need to be very expressive, the algorithms might be intelligent, and we're basically just going to let the verifier read all of the prover's secrets, okay? And so I'm going to decompose the tasks that the verifier needs to perform in order to check some statement into two different ones. The first is it needs to gather a trusted information set about what the prover is doing. And so I'm going to use this term throughout, so like read the definition. You can think of a trusted information set as just like, okay, imagine you could like see all of OpenAI's databases and just like read them, and you just trusted that these databases were a complete and accurate representation of what all of their compute was doing. Okay, that would be a trusted information set. The verifier clearly needs that. Okay, it needs accurate information, it needs comprehensive information, and then given that, then it has to perform task number 2, which is ensure that the semantics of this information are consistent with the statement. Okay, and then once it's done this, then it can just like emit its verdict. Okay, and so just going to walk through in more concrete detail what this might look like in 3 different settings. So in the first setting, we're going to assume the verifier starts with a trusted information set. Like it can just read the prover's databases and like all that information is good. And we're also going to set privacy aside. And then we're going to walk back the assumption that privacy doesn't matter, and then we're going to walk back the assumption that the verifier starts with trusted information. Okay, so in this first setting, the verifier just needs to check the semantics of the information it has about what the prover is doing. Okay? The only point I want to make on this slide is it's just unclear whether the verifier needs intelligence or in what way it needs intelligence. And so let's look at our training pods example. Clearly, the verifier needs intelligence in order to determine whether a bunch of inference outputs reflect like doing research to subvert the pause. Okay, so in that setting, you need intelligence. Maybe something like verifying that only inference is being run on a bunch of AI servers is something you can check just using simple programs, though. Clearly, you could check it using intelligence, but maybe you could do formal verification. So maybe we could agree to some spec for what inference looks like, and then just have the prover just issue periodic proofs that all the code it's running is in fact inference code and not training code. So we don't know whether it needs intelligence or not, or to what extent. Okay, so in setting 2, we're going to say that privacy matters. Okay, idea for how to do this. Incentivize zero knowledge. So here we're going to let the verifier see the prover's secrets, but we are going to somehow set up the system such that the verifier is incentivized not to leak any secrets. And so what I've done to this diagram is just one thing. I've made it so that the verifier is inside of a black box. Okay, just literally imagine like a little black box. There's an algorithm running inside of it, and it only has one outbound wire that just leads directly to this third party. And critically, the prover is guaranteed to be able to read the messages sent over this wire. And so if all parties in this setup agree that the prover would be highly likely to detect if the verifier was able, or if the verifier was emitting secrets inside of its verdicts, then at equilibrium, you should expect that the verifier would not leak secrets. And so this would be zero knowledge at equilibrium. Now, the key threat is verifier steganography, right? There are ways to undetectably encode information in a bit stream. And so to mitigate that, this system might need to be built such that the outbound channel from the verifier has a very low bit rate, okay? And this might be very sketchy from the third party's perspective. Like in one extreme, it might only emit 1 bit every day or something like that. And critically, intelligence is able to do steganography. So this suggests that there is a trade-off in this setup between having the verifier be intelligent and how much information is able to leave this little black box. Okay, so setting 3. Now the verifier needs to somehow figure out what the prover is doing. It doesn't have a trusted information set. So this is the problem, essentially, of figuring out what all of the AI accelerators are doing. And so this is what I've been working on mainly. So let's focus on the inference example. Suppose the prover issues cryptographic commitments to each inference record. So every time it runs inference, it sends the verifier the hash of the input, the output, and references to any model used. So just picture, like, from the verifier's perspective, it just sees this big list of hashes, right? And what it needs to do is check that these hashes correspond to correct inference records, they're not spoofed, and that it's seeing all of the hashes, that there weren't like other computations that the prover was performing that are not being shown. And so verifying accuracy seems totally tractable, okay? Even in a zero trust setting. Why? Well, because randomness is very powerful. So what you can do is the prover can publish its commitments, make a list of like n different inference jobs that it did. The verifier can pick k of these for a very small k. The prover can re-execute that inference job on its servers and then prove that the commitment was correct. It can issue a proof, okay? And so this is very expensive for it to do, but due to sampling, you don't have to do it that often. And so, for instance, the verifier only needs to verify 45 inference IO pairs to get 99% confidence that at least 90% of the n inference commitments are correct. And so for reference, OpenAI makes like 10 billion inference outputs every day. To check that at least 90% of them are correct, you only need to check 45 of those. That is so cheap. Like, this is completely tractable. Cost curves are fine, and you can do more efficient things for sure. Okay, so verifying comprehensiveness. This is a weird problem. This is a non-traditional problem. So we're going to set this up like this. Suppose the verifier has counted all of the prover's accelerators and that each accelerator, so the accelerator is a GPU, tells the verifier every time it performs an operation. So if I'm an accelerator, I perform a matrix multiplication, I'm going to tell the verifier with a timestamp. Okay, so the verifier needs to check that each accelerator is only doing what it claims to be doing. And so one way you could do this would be to render it exceptionally inefficient to perform undeclared computations interleaved or in parallel with your declared computations. And maybe you can do this by exploiting unavoidable physical properties of computation, so maybe you can get some nice security guarantees. And so in some ongoing work, in a paper called Interactive Memory Attestation, we rely on the following property. So if an honest accelerator is performing its workload the way it claims to be, well, it's going to have like particular unique state in memory every single time, or at every point in time. So suppose this accelerator is performing inference. Each of these colored squares corresponds to some unique set of activations that it should have in its high bandwidth memory if it were performing the workload that it claims to be performing at the times it claims to be performing it. And a dishonest accelerator would not look like this. It would have different state in memory at different points in time. And you might be able to distinguish between the honest accelerator and the dishonest accelerator by situating a trusted device right next to each accelerator and have it constantly challenge at a very high frequency each accelerator to produce a time-dependent hash of the state that it currently has in memory, okay? And so the assumption here is that an honest accelerator would be able to produce a hash of its state very quickly because it has it in memory. A dishonest accelerator would not be able to produce a valid hash. It would take time to compute honest state. So this is the state that it should have in memory if it were performing its workload as claimed. Or maybe it could fetch it from a cache. Okay, and so ongoing work is basically trying to figure out how we can set up this trusted device such that it can set a very tight latency tolerance on responses from each accelerator so that it can distinguish between honest accelerators and dishonest accelerators. So these hashes can be verified asynchronously as part of the verifying accuracy that I was just talking about. And so in particular, the takeaway here would just be if an accelerator is claiming to be performing inference on model X, given a protocol like this, it seems exceptionally difficult for it also to be performing undeclared training, right? Because training requires a bunch of memory. And so if you're running inference on model X, hopefully you can't be running training on model Y without declaring it. Okay. Pitch, you should work on this. It's very cool. There's like 20 people working on it. There's a QR code.
All right. Yeah, give it applause. Applause for Daniel. And we've got time for one final question for the final talk. Hands up if you have a question.
Could you explain in a bit more detail like the different requirements for like verifying a semantic component versus verifying just whether like the inference has been properly done? Like if you want to do some additional level of verification that the model or the GPUs are not being used, let's say, for bioweapons capabilities or something, and this is part of your treaty about what they're doing, what additional work do you have to do compared to like just verifying inference?
Okay, so there's again like two tasks here. The verifier needs to check kind of like that the information that it gets is good. So one way it could fail to do the thing you're describing is that it could fail to attain complete information about what's going on, and this information it doesn't know about could be making bioweapons or whatever. So doing kind of like low-level computational verification hopefully enables it to avoid that. Okay, but maybe you're talking about the more semantic thing where like it knows, like it can see all the inference outputs or whatever that are in question, but it needs to figure out whether they're good or bad. Yeah. Probably you just need to use models. I think you just need to use models.
All right, can we have a round of applause both for Daniel and for all of our speakers? We've had a bunch of awesome speakers today. It's been great.